Hi there, and welcome to part 4 of my read and work through of Generating Functionology by Herbert Wilf. If we remember last time, I was looking at the example at the end of section 1.4 where we were looking at fitting the powers of 2 to this cubic spline of cubic functions which are continuous and have continuous first derivative when you combine them all together, and also continuous second derivative. And I was trying to find a nice easy way of calculating the values u1, u2, u3, u4, because I'd found fairly nice easy ways to do u1 and u4 if we see the end of the last video. So I spent a little bit of time investigating this, and I worked out, realised what I was doing could be generalised back to the case that we worked through at the start of the chapter, the start of the section, sorry, the free term value boundary problem, where you have the relation a u n plus 1 plus bun plus cun minus 1 equals d. This dn, this was a setting we had, and we had it such that if we take the quadratic cx squared plus bx plus a, then if this has two roots, r plus and r minus, and if nth powers of the two roots are different, where we had n minus 1 different equations here, then we were able to get a unique solution. So I started looking back at with this notation and reintroducing the a, b and c instead of the case that we had where our a was equal to 1, b was equal to 4, c was equal to 1. So that case was a little bit nicer, but you could do it in a little bit more generality. It's always nice to do that when you can. So let's work through that a little bit. I'll not go too much into depth. I'll skip over a few things, and I'm going to add the working I've done on this to the end of the PDF document I wrote in the second part of this series, where I covered this case in more detail. So I thought this, is a good thing to add on to that. So I'm going to link to that at the bottom, so you can go through everything in a little more detail if you want. So let's continue. I'm going to apologise now because I've got a cold, so if I'm sniffling a lot and if I sound croaky, then that's why. I've had a lot of colds lately. This is my second one in a couple of months. It's very annoying, and I've also had a tooth infection in that time, so it's not been a very good month for my voice. Right, let's see. So if we recall, going back to the setup at the start of this section, we had this equation. So we had ux over x equals dx plus a u1 plus cu n minus 1 x to the n, if we recall, where the function ux is polynomial summing from I equals 0 to n, ui x to the n, ui x to the I. However, u0 and un was 0, so we might as well consider this as being from 1 to n minus 1. And furthermore, function d, polynomial dx to find I equals 1 to n minus 1 di x to the I. So we had these, and we were searching for the u's. We were given the d's. We were given n. So we're given n minus 1 powers of d, and these n minus 1 simultaneous equations, and we're after finding u1 to un minus 1, and we say that u0 and un are 0. I'm trying to solve this for the u's. So we had this form, and for the time being I'm going to, this here itself is a polynomial. I'm going to call this polynomial gx, and I'll write gx as sum from I equals 0. I'll write to infinity of gi x to the I. So we would have that g0 was equal to, this is the constant part of this polynomial here, so this bit is g0. This term is going to be, so c un minus 1 is going to be gn. That's the only time x to the n appears in this polynomial here, and gi is going to be equal to di when I is between 1 and n minus 1. But I'm just going to write it in this form here, and obviously for n bigger than big N, then gn is going to be 0, but I've just written it in this form for convenience later on. I've missed something out here. We had our quadratic as well, so we had the cx squared plus bx plus a was a factor, so we had this quadratic times ux over x equals this thing on the right. So what we have is that ux is equal to x over cx squared plus bx plus a times gx, and we will want to express this in terms of a power series. So I'm going to use sequence Vn, define the sequence Vn by x over cx squared plus bx plus a equals n equals, I shouldn't probably use, no, I use n equals 0 to infinity Vn x to the n, and this will define our sequence Vn. And so then we have that ux is this product, sum from n equals 0 Vn to the n times sum from n equals 0 to infinity gn x to the n. And we can combine this product here by collecting powers of x. So the only constant term is going to be v0 g0, so v0 g0. The only terms with a linear factor of x is when, say, you've got 0 in here and 1 on this side, so v0 and g1, or a linear factor on this side and a constant factor on this side, so you could also have v1 and g0. So your next term would be v1 g0 plus v0 g1 x. And if you wanted to get your x squared terms, the next one, you could have 0, a constant term on this side, a square factor on that side, a linear factor on this side and a linear factor on this side, or a quadratic factor on this side and a single factor on this side. So you're going to have v0 g2 plus v1 g1 plus v2 g0 x squared plus, and so on. And so to sum this up, it's going to look like sum from n equals 0 to infinity x to the n, and then you've got the coefficient of x to the n. Well, that's going to be, so a sum from I equals 0 to little n, of gi v n minus I. So it's all pairs of coefficients whose index sums to your n here. And this is how it works. So, you know, if we have a gi x to the I times a vn minus I x to the n minus I, their product is going to be gi vn minus I x to the n. So we have this here. It tells us what ux is, and we know what gi is already, because I pointed out, you know, it was just this thing here, and we know that ux is going to be a polynomial. We know u0 is 0, we know un is 0, so we're only interested in the terms between 1 and n minus 1. So we're interested in knowing u1, u2 to u n minus 1. Therefore, we never need to worry about this gn term. We only need to worry about the other terms that occur as coefficients of x to lower powers than n. So let's write this out again. So we're going to have, so this is ux here, ux. Move that way a little. So if I want to know un, so say I want to know some n for n in between 1 and n minus 1. These are the ones we're interested in. So un is going to be the coefficient of x to the n here, so which is going to be sum from I equals 0 to n gi v n minus I. We know that g0 is equal to, it was au1, and gi is equal to di for I in the between 1 and n minus 1. And since n is less than n minus 1, this is going to be equal to g0 vn plus sum from I equals 1 to n gi di, sorry, the n minus I, and g0 was a un, so au1. So this here, once we know what u1 is going to give us a formula for un. So un will be au1 vn, I'll just write it out a little neatly, sum from I equals 1 to n di vn minus I. So now we've got un in this form here. Next question is, well, what is u1? And we did this before. It is a to the minus 1, there's r minus to the n d r plus minus r plus to the n dr minus r plus to the n minus r minus to the n. I think that's right, though I could possibly have a sign error. Let me check. A minus r minus to the n. Yeah, that's right. So this was our u1 here. And if we, as I did at the end of the last video, we can expand out these terms here, because dx is just the sum of di and x to di. So expand this out as follows: a to the minus 1 sum from I equals 1 to n minus 1 di, and then times everything that di is a factor of. So r minus to the n, r plus 2vi minus r plus to the n, r minus to the I over r plus to the n minus r minus to the n. So plugging this back in then, so this is our u1, well au1 is going to look like, we can lose these a minus 1s, and vn times au1, we're just going to shove vn out here. Okay, so we have that un equals this thing, r plus to the I minus r plus to the n, r minus to the I, all over r plus to the n minus r minus to the n. And then we had plus I equals 1 to n di vn minus I. And then this raises a question: what is v? What is this sequence v? We just defined this sequence v as that sequence of numbers such that c squared plus bx x over c squared cx squared plus bx plus a is equal to the power series vn x to the n, x n equals 0 to infinity. This is how we defined it. So we've not explicitly calculated vn, but we can do that, and we can expect this sequence vn to have to involve these powers here, because we've seen some examples like this before, and it involves the root. It involves the roots of these guys, and you know it's going to look something along these lines, isn't it? So let's quickly calculate what the vn's are. So we're looking at x over cx squared plus bx plus a, and we know this has two roots, r plus and r minus, and their nth powers are different, so the two roots are going to be different, which is good for when we expand it into partial sums. So let's call the roots r plus and r minus, and it's going to be equal to c times r plus minus x, r minus minus x. Now, we can expand this into partial sums. I'm not going to bore you through it all, because we've done this sort of thing already, and I don't want to spend too much time on this, so I've already computed it. Let me just look it up. So it's going to equals 1 over c, the difference between the roots, so r minus minus r plus, times the sum from I equals 0 to infinity, r plus to the minus I minus r minus to the minus I, x to the I. If you're interested in seeing how this is derived in detail, you can look at the PDF document I'm going to link to at the bottom, though we've already done this sort of thing before in earlier videos. So this tells us that Vn is equal to the coefficient of x to the n here, so it's going to be r plus to the minus n minus r minus to the minus n over c r minus minus r plus. Yeah, that's fine, that's right. So now let's try plugging, well let's examine what we had before for our expression of un. Where's it gone? So we had un here. So rather than expand this vn minus I part out, I'm going to try and express this term here in terms of the vn, because I'm expecting that to be a little bit more compact, because just writing vn is more compact than write in our expression for Vn. So let's try and take this bit apart here and see if we can get that to look like Vn. So I am looking at the quotient r minus to the n, r plus to the I, minus r minus to the n, r minus to the I, over r plus to the n minus r minus to the n. And we had Vn is equal to 1 over c r minus minus r plus times r plus to the minus n minus r minus to the minus n. So what can we do to this form here to utilise this? Well, first thing I'm going to do is I've got a slight problem here that we've got r minuses coupled with r pluses. So first thing I'm going to do is divide the top and the bottom of this equation by r plus to the n, r minus to the n. So this is going to become r plus to the minus n, r plus to the I, minus r, that should have been a plus, r minus to the minus n, r minus to the I, over, so I've divided the bottom bit by r plus to the n, r minus to the n as well, so it's going to become r minus to the minus n, minus r plus to the minus n. So now we have r plus I minus n, minus r minus I minus n, over r minus minus n, minus r plus minus n. So now we see we've got negative exponents everywhere. This is I minus n, that's negative because n is bigger than I, and minus n is negative. So, and we see that the Vn, definition of Vn here, has negative exponents. So what this is just going to be is, it's going to be V n minus I over Vn. And there's going to be a negative here since we've got a plus and a minus there and a minus and a plus here. And the reason it's just Vn minus I over Vn is because the 1 over c r minus minus r plus bit is going to occur in both Vn minus I and Vn, so they cancel out. So that's a much more nice looking compact version of this. So let's plug it back in to un. So we have that un is equal to this thing, so un equals Vn I equals 1 to n minus 1 di, and this whole term here is V n minus I over Vn, and we needed a minus, so it becomes minus, and then we can add on the last little bit here, sum from I equal 1 to n di Vn minus I. So this is looking much nicer now. Now we've got something we can work with a little bit here. We've got rid of all the complicated large powers of ours and that sort of thing. We've just got a nice succinct formula here involving only the sequence Vn's. So let's rearrange this a little bit further. So I do want a nicer form in the end. So un equals, so what I'm going to do here is I'm going to start off by grouping the first n summands in this sum here with this sum here, because you've got d1 to dn minus 1, but we've only got d1 to dn here, so I'm going to combine the first d1 to dn. So this is equal to I equals 1 to n of minus Vn that I've just got di on the outside minus vn v big N minus I over v big N plus vn minus I, and then because we've only taken the first n summands of this, we also need to add on the rest, so plus I equals n plus 1 to n minus big N minus 1 di v n minus I over v big N, and we also needed minus vn out here. Change the plus to a negative here. So, and I want everything to be over v big N, because we've got a b big N here, b big N here, and in the example we were playing with, we ended up with this being the denominator of the fractions that we were trying to get to in the end. And what we ended up doing when we were calculating in the live example, we had this quotient over v big N, which was 209 in our case, and then we were adding on an integer, and that calculation, if you're going to do it by hand, would involve multiplying a number already fairly large by potentially fairly large by 209, and then adding it together and then redividing by 209, and yeah, it wasn't very nice. So I was searching for a more succinct form. So what I'm going to do is I'm going to take out the 1 over vn, v big N, and then we have sum from I equals 1 to n di vn minus I v big N, so I multiplied this bit by v big N because I'm dividing it by here, I need to correct for that, minus vn minus I. This already had the 1 over vn in, so I don't need to multiply this by vn, minus vn sum from I equals n plus 1 to big N minus 1 di vn minus I over v, oh no, not over vn, so because we've got the vn out here, so got this form here. And this term here can be represented in a completely different form. It turns out that this term here is equal to c divided by a n minus I, that's negative of it, v n minus n vi. So I'll discuss this a little more shortly, but let's just take my word on it for now. We end up with the final formula of un equals 1 over vn, v big N, sum from I equals 1 to n minus di c over a n minus I vn minus n vi minus vn sum from I equals n plus 1 to n minus 1 di vn minus I. And I can take out this vn minus n here to the outside of this sum because this doesn't depend on I. So finally, sum from I equals, oops, I want to take out, so v n minus n, sum from I equals 1 to n, c over a n minus I di vi minus vn, so from I equals n plus 1 to n minus 1 di v n minus I. So here's our formula. And in the live example we were doing with the for the powers of 2, the c and a were both 1, so this factor just becomes 1. And you've got a fairly simple equation then, once we know what these v's are, and which in that case it was an integer sequence, it was easy to compute. Though in this form I'm not too happy with this term here, this c over a to the n minus I. I feel like perhaps there should be a more symmetric representation where it's just similar on both sides, or maybe I can use a different sequence in the v's somehow, tweak it in some way to get something looking a little more symmetric and nicer here, but I'm happy with it the way it is, just about, because it suits for my needs. I only needed it for the example we were doing at the end of section 1.4, and this is the solution to that, but generalised to the case where we've got the coefficients a, b and c instead of 1, 4 and 1. So I'm happy with this for the time being. So the white elephant in the room here was, how did I do this bit? How did I combine these? And it's not too hard to prove this identity, but it is a little bit fiddly. So I'll do it quite quickly, and I won't go through all of the horrible details of it. So what we want to do is we want to prove this identity: c divided by a to the n minus I, vn minus n vi equals vn v big N minus I minus vn minus I vn. And I spent quite a lot of time playing around with identities involving the sequence v, and I had quite a bit of fun doing it, and then eventually I got to the bottom of this formula, and it took me a while, and at first I didn't quite know what I was doing. I had some identities and I was like putting them together, and I didn't have a very good feel for it, so I don't think it's going to be very easy to explain that, in a very nice way. First thing we should probably note is that this sequence vn is going to follow a recurrence relation. It's got a simple recurrence relation to it based on the fact that vn, it was basically equal to a constant, which was 1 over c r minus r plus multiplied by r plus to the minus n minus r minus to the minus n. And here we have negative powers of roots of unity of the following quadratic: cx squared plus bx plus a. And every root of this quadratic is going to, say if r is root of this quadratic, we're clearly going to have cr squared plus br plus a equals 0, and if we multiply through by a power of r, similarly have crn plus 2 plus brn plus 1 plus a r to the n equals 0. And this here gives us a recurrence relation for powers of r. So you have that crn plus 2, and if we know r to the n plus 1 and r to the n, it's minus b r to the n plus 1 minus a r to the n. So, and we know that, you know, r to the 0 is going to be 1, and r to the 1 is r. I'm assuming we know what r is. But v is a linear combination of not r roots to the n, but negative powers. So as we increase n, we're actually decreasing the power here. So we need to look at it the other way. So instead you could say, well, if we divided this equation here by r squared, you would have c plus b r to the minus 1 plus a r to the minus 2 equals 0. And if you're looking at negative powers, you could have c r to the minus n plus b r to the minus n plus 1 plus a r to the minus n plus 2 equals 0. And so this gives us a recurrence relation for the negative powers of r. So a r to the minus n plus 2 equals minus b r to the minus n plus 1 minus c r to the minus n. And since vn is a linear combination of roots of this quadratic to negative power, Vn will also satisfy this recurrence relationship. That gives us a recurrence relationship for n. So you have that Vn plus 2, or a Vn plus 2 equals minus b Vn plus 1 minus c Vn. Nice recurrence relation there for V. And from this formula here, we can explicitly calculate that V0 is equal to 0 and V1 is equal to 1 over A. And yeah, that's easy to do. You plug it in and use the fact that C times R plus times R minus is equal to A. It comes from the fact that R plus and R minus are the two roots of the quadratic. So now this allows us to describe V, and we've got this recurrence relation, so we can start playing around with identities. And so basically I started with the identity, you start with the basic one, C Vn equals minus A Vn plus 2 minus B Vn plus 1. And if then we take this Vn plus 1 and substitute in and use the next equation, which is CV n plus 1 equals minus a Vn plus 3 minus b Vn plus 2. So if we use this equation here to write Vn plus 1 in terms of Vn plus 2 and Vn plus 3, we can then express Vn in terms of Vn plus 2 and Vn plus 3. And doing this repeatedly allowed me to get the following lemma, which I'm not going to prove. It's easy to prove by induction once you make this observation that this is how you generate it. So for all n greater than or equal to 0 and k greater than or equal to 0, we get that ck over ak plus 1 Vn is equal to Vk plus 1 Vn plus k minus Vk Vn plus k plus 1. And this is essentially what we get doing this repeatedly, since when k was 0, you're going to have if k is 1, you've got this Vn plus 1 here and a Vn plus 2, and we've already got it expressed in terms of Vn plus 1, Vn plus 2. And if we did a substitution, we get it in terms of Vn plus 2, Vn plus 3, that's the k equals 2 case. So just for a quick check, I'm going to do k equals 0 here. If you plug in k equals 0, you get 1 over a Vn on the left hand side. Is that equal to the right hand side? You get V1 Vn plus k, which is Vn, and minus Vk, which is V0, and V0 is 0. So, and we know that V1 is equal to 1 over a. So it works for k equals 0. And it's easy to prove by induction that it works for all k, for all n as well. And then from that as well, I also was able to get actually no, not from this, I did this separately, but I feel it's related, and maybe there's a way to prove this second result from this first result. Is rather than constantly trying to express Vn in terms of Vn plus something and then Vn plus something plus one more, so Vn plus k and Vn plus k plus 1, what I instead tried to do was express Vn in terms of Vn plus 1 and Vn plus k. So I was kind of doing it the other direction, kind of. So, and then you can just do the same thing backwards to kind of get that. So if you start off with the equation a Vn plus 2 minus a Vn plus 2 minus b Vn plus 1 equals CVn, and instead I use the next equation, minus a Vn plus 3 minus v bvn plus 2 equals cvn plus 1. And if I use this to write the vn plus 2 in terms of the vn plus 3 and the vn plus 1, I'll get something vn is equal to something times vn plus 1 plus something times vn plus 3, and if I continue I can get vn equals something times vn plus 1 plus something times vn plus k. And doing that leads me to this result, that for all n greater than or equal to 0 and k greater than or equal to 0, we have vn plus k plus 1 equals a vn plus 1 vk plus 1 minus c vn vk. And so this is your vn term, the vn plus 1 term, and this is the vn plus 1 plus something else term. And you get this just by doing this, constantly substituting in the next one and doing induction that way. So here's another identity, and combining these two identities, so I had this one, vn plus k plus 1 equals a vn plus 1 vk plus 1 minus c vn vk, and the first one was, just write it out again, so c to the k over a to the k plus 1 equal vn equals vk plus 1 vn plus k minus vk vn plus k plus 1. And combining these two, it's possible without using induction this time, just a bit of messing around in algebra and jiggery pokery, to prove this more general result, which generalises to both of them, that for all n greater than or equal to 0, k greater than or equal to 0, m greater than or equal to 0, that c over a to the m vn vk equals vn plus m vk plus m minus vm vn plus k plus m. And if you set n to be 1 in this, you basically get this one, this crops out here. And if you set either n or k to be 1, you get this identity here. So that's why it generalises both of them. But it's just more useful in this form. And doing this and making some substitutions. So I'm just going to do the substitutions here to get it into the form that we wanted. So what we were after earlier, well, we had, what did we have? Let's see if we can find it. Our form for, yeah, here we are. We had that un was equal to this thing, and I said that this part here was equal to this here, and it's this result here that we use to show that. So I'll just quickly go through that. So what we're trying to show, what we wanted to show was that c over a to the n minus I v big N minus n vi was equal to vn vn minus I minus vn minus I v big N. And so notice here that we have some minus things occurring, but it's no big deal because little n is smaller than big N, and I is smaller than n, and I is smaller than little n. So it's fine, we shouldn't have any problems here. So what I do is, first thing I'll do is in this equation here, is I'm going to replace n with n minus m, assuming that n is going to be bigger than or equal to m. So you get c over a v n minus m vk equals v n minus m plus m, so just vn, v m plus k minus vm v n plus k plus m, but n has now been replaced with n minus m, so it just becomes n plus k. Now this is already looking a bit more like this, because if we've got a vn here times vn plus k, well, we've got n plus I, and then we've got a vn here and a vm here, and so you've got two terms on their own, the vn and the vn, and here you've got the vn and the vm, and then we've got another two terms which are the other one with something else subtracted. So here we've got the vm with the k added, so it's slightly different. But what I'm going to do to this equation here now is I'm going to replace both n and m. I'm going to reduce them both by k. So this will become c over a m to the n minus k. N minus m is still going to be n minus m. K stays the same. Vn minus k, vm minus vn minus k, vn. Now this is looking very much like the thing here that we want. And now just making the right changes. If we change m to, let's see, if we change m to little n and little n to big N and k to I, we get exactly this here. So that's a very, very quick guide as how you get that result. So now we have this form for un, we can go back to apply it to our setting in our example in the book, which was making a cubic spline to the first 6 powers of 2, from 2 to the 0 to 2 to the 5. So we had slightly different notation then. We had, I think, ZNs instead of UNs, and I was using UN instead of the V's that I've got here, but it's not a problem. So if and we know that C and A are going to be 1, so let's write it out in this form. In the old notation it's going to be Zn equals, and I was using U's instead of V's, so I'll go back to the U's. U n minus 1, n to the minus 1. Oh, and also big N was little n, wasn't it? But I'm just going to keep big N and little n. Avoid too much confusion. We have minus u big N minus n, sum from I equals 1 to n, and this is just 1, di vi minus un, I equals n plus 1 to n minus 1, di v n minus I. Well, big N was 5, wasn't it? It's because we were plotting, we were trying to calculate Z1 to Z4 and Z5 and Z0 above 0. So that means big N is 5. So this is u5 to the minus 1 plus minus u5 minus n, sum from I equals 1 to the n, di vi minus un, sum from I equals n plus 1 to 4, di v5 minus I, not u, not v's. These are all u's, not v's. And if we remember the sequence u, well, it's satisfied the recurrence relation un plus 2 equals minus 4 un plus 1 minus un, and u0 was 0 and u1 was 1. So this meant that we had u2 is minus 4, u3 is 15, u4 was minus 56, u5 was 209. And for D's, if I remember rightly, were DI, it was 6 times 2 to the I minus 1, I think. That was what we had. So I can now just plug this straight into the formula for Zn. So let's see. Let's try U1, so Z1. Z1. I'm just going to write the years out here again. So 0, 1, minus 4, 15, minus 56, 209. These are these guys. So Z1 is going to be U5 to the minus 1, so 1 over 209 times. Now, minus 5 minus n, well n is 1, so it's going to be minus U4 times the sum. I equals 1 to n, and n is just 1, so it's going to be D1 times U1. The D1 is going to be 6 times 1, and U1 is 1. And then we've got minus UN, so minus U1, and U1 is just 1, times I from 2 to 4, di, so 6 times 2 to the I minus 1, U, 5 minus I. So this bit here, so let's write this like this, is 1 over 209, so minus, I'm going to take 6 out here, minus U4, and then I can get rid of the 6 here as well, minus I equals 2, I'm going to have 2 U3 plus 4U2 plus 8U1, and that's it, right? So let's check if this was right. So it was 6 over 209. So let's plug the values in. U4 is minus U4 is 56, minus 2 times U3, 30, and then it's going to be minus 4U2, so plus 16, then minus 8 is equal to 6 over 209. Let's type it all in. 6 minus 30 plus 16 minus 8 times 34. And 6 times 34 is 204, yeah, and that was right, that was 204 over 209. So, yeah, it's working, it's good. So we'll try and calculate Z2 using exactly the same formula. So the formula is, going to put the Zn back, so we'll have Z2 equals U5 to the minus 1, that's going to be 1 over 209, minus U5 minus n, so minus U3, sum from I equals 1 to 2, so that's going to be D1 U1 plus D2 U2, and then we're going to have minus UN, so U2 minus U2 times the sum from I equals 3 to 4. we're going to have D3 U5 minus 3 2 plus D4 U1. So let's plug in the values. We're going to have, so it's going to be 1 over 209. U3 was 15, so minus 15. I'm going to take the 6 out because DI is always got a factor of 6 in. So this is going to be 1 times U1 minus 2 times U plus 2 times U2, so that's minus 8. Minus U2, so that's plus 4. D3 U2, so 4 times minus 4, plus D4 plus 8 U1 times 1. So let's calculate this. This is 6 over 209, so it's minus 15 times minus 7 plus 4 times minus 16 plus 8 equals 6 over 209. I'm going to put it into the calculator. 15 times 7 minus 4 times 16 plus 4 times 8. So I get 73 here. And 73 times 6 is 438 over 209. Is that what they have in the book? 438 over 209. Yeah, brilliant. It seems to be working. And just try Z3 and Z4. So will Z3 be using this formula again? Got Z in there, so now Z3 is going to be equal to 1 over U5. So n is 3 now, so minus U2, and now I goes from 1 to 3, so D1 U1 plus D2 U2 plus D3 U3 minus U3 D4 U1. That's all we have this time. So it's 1 over 209. I'm going to take the 6 out because there's a factor of 6 in every DI. So minus, I always constantly need to remind myself what the U's are. So U0, U1, U2, because I forget the signs. So we had 0, 1 minus 4, 15 minus 56, 209. So minus U2 is going to be 4. I'm going to have U1 minus 2 times U2, so just plus 2 times U2, which is minus 8, plus 4 times U3, plus 60, minus U3, so 15 times D4, which is going to be 8 times U1, times 15 minus 8. What's this going to be equal to? So 6 over 209 times 4 times 1 minus 8 plus 60 minus 15 times 8. I get 92 here. So what's 6 times 92? 552 over 209. Is that what they have for Z3? Yes, it is. Brilliant. Fantastic. And last but not least, let's check it works for Z4. Do I have any paper? Yeah, a bit here. Look, got the Zn formula again. So Z4 equals U5 to the minus 1. Now we have a sum from 1 to 4, and this term won't take part at all because it'll be going from 5 to 4. It's an empty sum. So we're going to have minus U1, sum from I D1 U1 plus D2 U2 plus D3 U3 plus D4 U4, which is equal to 101 over 209 times minus U1. Take 6 out for all the DI's, so we're going to have DI U1 times plus 2u2 minus 8 plus 4u3 plus 60. Wow, it's big numbers. Minus 8u4 minus 8 times 56. So what do we get here? We get minus 6 over 209 times 1 minus 8 plus 60 minus 8 times 56. Minus 395 equals 2370 over 209, which is right. So yeah, that was it. That's how to relatively a nice simple formula for calculating not just Z1 and Z4 but Z2, Z3 as well. Once you've calculated your sequence UN and sequence DI, then it's fairly easy to plug everything in, and none of the calculations here are too hard to do. It's much easier than the way we were trying to do it before, using the recurrence relation, because we were adding integers to a fraction with 209 as a denominator, and yeah, worked out quite nicely. So now we've finally got that done, we can go back to reading the text. So I've calculated Z1 to Z4 and it agrees with what they've done. So now we know all of the ZI's. Finally, 1.4.7 tells us the exact cubic polynomials that form the spline. For example, S0, which lives on the subinterval 0 to 1, is S0x equals 1 plus 175 over 209x plus 34 over 209x cubed. Right, so what was the formula for SI? Let's see what these look like. Get SI x. SIx equals 1 over 6h. H is 1. I'll just write this out like this first. Zi ti plus 1 minus x cubed plus zi plus 1 x minus ti cubed plus 6yi plus 1 minus h squared zi plus 1 x minus ti plus 6yi minus h squared zi ti plus 1 minus x. So let's plug in what we know. So SI x equals 1 over 6, h is 1, zi, t is just, ti plus 1 is just I plus 1, I plus 1 minus x cubed plus zi plus 1, x minus I cubed plus, now y I is 2 to the I, so we got 6, 2 to the I plus 1, 6 times 2 to the I plus 1, minus zi plus 1, x minus ti, I'll run out of room here, x minus I, plus 6yi, that's 2 to the I, minus zi, I plus 1 minus x. So let's see what this is. In the case I equals 1, see if we agree with what they've got written. It's like a particularly simple polynomial that they get. So S0 x should be equal to 1 over 6 Z0, which is 0, so I'm not even going to bother writing the next term, plus Z1 x minus I, that's just Z1x cubed, plus 6 times 2 to the I plus 1, so that's 6 times 2 minus Z1 times x minus I, it's just x. Then we have plus 6 times 2 to the 0 minus z0, which is 0. So it's just 6 times 1 minus x. That term is 0. So it's 1 over 6 z1x cubed plus 12 minus z1x plus 6 1 minus x. Oh, sorry, went off the screen there. So let's divide out 1 over 6. That's z1 over 6 x cubed plus 2 minus z1 over 6 x plus 6 minus so divided by 6, 1 minus x. Right, what was z1? Z1 was 204 over 209. 204 over 6 is 34, so that's 34 over 209 x cubed plus 2 minus 34 over 209 x plus 1 minus x. That's 2 there. Well, we have a minus x here and we have a 2x here, so I'm going to kill that and change that 2 to a 1. We've got 1 minus 34 over 209. That's relatively easy to deal with. So we'll have 34 over 209 x cubed plus 209 minus 34 over 209 x plus 1 equals 34 over 209 x cubed plus, what's this going to be, 175 over 209 x plus 1. Well, does this agree with what they had? They had 1 plus 175 over 209x plus 34 over 209x cubed. Yeah, correct. Alright. Well, I'm not going to bore you with calculating the values of S1, S2 and so on. But what I might do is I'll calculate them on my own, and I'd like to plot them. I'd like to see what it looks like, how smooth this graph looks, because it should look pretty smooth. You know, it's derivative and second derivative are going to be continuous, so only when you get to the third derivative it's not going to be a continuous function anymore. So yeah, I'll work these out and see what we get. So I've calculated all of the functions S0 to S1. Now I've checked they all work. And these are the values of derivatives at the ends of each segment and the second derivatives, and see that they all equal the right things here. Now I've drawn a few graphs. So here we've got a graph of all of them connected together, and you can see they fit together perfectly, and it looks really smooth. It looks really nice, and you can see from the graph that they equal the right things, the right values. At the origin it's 1, at 1 it's 2, at 2 it's 4, at 3 it's 8, at 4 it's 16, at 5 it's 32. And here I've plotted the cubic spline against the actual function 2 to the power of x. So the black line is 2 to the power of x, and the blue line is our cubic spline, and you can see it fits it really well between 0 and 5, which is where we've calculated it for, and it still fits fairly well between, say, 0 and minus a half. But as you can see, it's diverging there around -1, and you can see it starts to diverge a lot after 5. You also see it's not quite so good around 4.5. it's diverging away from the curve a little bit there as the exponential graph gets very steep. Now I've plotted all of the 5 cubics together here, just so you can see, or partially see, how they all kind of fit together along the curve of the graph, and I think it looks pretty cool. And our graph is supposed to have points of inflection at the ends as 0 and 5. So I've drawn in the gradients here, and you can see that the line of gradient cuts through the graph just about from this picture, which is what's supposed to happen at an inflection point. So here I've plotted the derivative of all of them, and you can see that the derivative is a continuous function, which is what we're supposed to have. There's turning points at 0 and 5, which is what you'd expect since there's an inflection point there. That's what it means. The derivative is equal to 0 at those points. Oh, it's a turning point. So, and here's the second derivative. We see that it's 0 at 0 and 5. Sorry, before I said that an inflection point meant the derivative 0. No, it means the derivative of the derivative 0. So that's why there's turning points at 0 and 5 on the graph of the derivatives there. And here we have a graph of the second derivatives. You can see it's still continuous, but it's certainly no longer differentiable. It's quite spiky. And obviously, if the second derivative was also differentiable and continuous as well, then it would mean that the third derivative of a cubic, which is constant, would have to be equal for all of the cubics S0 to S4, and then we would get from that the derivative must be the same, and you would end up with all the cubics are the same. So you would not expect that unless the points you're approximating already lied against one single cubic. Then that would happen, I suppose. And the cubic would have to have inflection points at the ends too for it to work. So yeah, there we go. I'm going to stop there. I'm going to leave it for today. I've not quite finished section 1.4 yet. It's taking me absolutely forever to get through 1.4, but yeah, I'm doing a pretty thorough job, but I don't really need to be doing it this thoroughly. After all, this section on cubic spline functions, it said in the book, you can skip this on a first reading. It's just a specialised use of the type of simultaneous equation that we introduced over at the start, which we could solve using generating functions. But I've had quite a bit of fun doing it, and I'd never heard of cubic spline functions, and in drawing those graphs that we just saw, I used Sage, which seems to be really good. I've never heard of this before. It's got a website, sagemath.com, I think it is, or something like that. I'll put a link to it underneath, and it seems great. It's basically, it seems to be a powerful mathematics software that's free, and you can use it online even without installing it on a computer, which is how I drew these graphs. So yeah, and in using that, I'd never heard of cubic spline functions before, and looking at the documentation about drawing graphs, plotting graphs with this, I saw that it had spline options, so that if you're plotting a graph, it can smooth it out using cubic splines. So there you go, you know, learn something new, and then straight away find it somewhere. So yeah, so I'm going to leave it there for today. I'm going to say goodbye. Thanks for watching. Tune in again next time, and I will hopefully finish section 1.4, shouldn't take me too long, and then get on section 1.5, which is looking, I'm quite excited about 1.5. We've got these Pascal's triangle coefficients cropping up, so that looks like it'll be quite fun. So, see you next time.